Happy Tuesday, y'all. So once again, we're starting with a warm-up. This warm-up, because it is balancing reactions, which we covered in the last video, I highly recommend getting out a piece of paper and actually solving your answer on paper. This is some math. It's simple math. It's multiplication or addition, depending on how you work it out yourself. But I still strongly recommend you work it out on paper. The first one is a little bit more straightforward. The second one, it is pretty challenging. Just remember those rules we went over yesterday. They are really important for the second one. All right, I'm going to stop talking and let you pause the video, work out your answers before I go over the solutions. Okay, so I'm going to start with the first one. I've got my pen, I've got my red ink. Okay, so let's look and see what is in my first reaction. I have iron, Fe. I have NO3. I have sodium, and I have hydroxide. So notice I have oxygen there, but I'm not counting oxygen as its own thing, since oxygen is part of a polyatomic both times I see it. All right, so I start with 1 iron, 3 nitrates, 1 sodium, and 1 hydroxide. Then on the other side of the equation, I have 1 iron, 1 nitrate, 1 sodium, and 3 hydroxides. Now, if you broke up the oxygen, this is going to be a bit of a headache for you to solve. That's why it's best to just keep it as polyatomic ions. So my irons are balanced, nitrates are not, sodiums are not, hydroxide is not. Okay, I don't have any carbons to choose from, so there's no one I have to start with. And I don't have any oxygen by itself, so there's no one I need to end with. So I can start balancing whoever I feel like. So I'm going to start with my nitrate, because going down this list, it's the first one that's not balanced. I have 3 nitrates on this side, 1 nitrate here. So I'm going to put a coefficient of 3 here. So 3 times my 1 nitrate gives me 3 nitrates. But there's also a sodium here, so 3 times my 1 sodium gives me 3 sodiums. Shoot. Okay, my nitrates are nice and balanced, but by balancing my nitrates, I've unbalanced my sodiums. So I'm not going to go and now balance my hydroxides. I'm going to focus on my sodiums. I'm going to try and fix what I just broke. All right, so I have 1 sodium here. I need to make it 3 sodiums. So I'm going to give it a coefficient of 3. So now my 1 sodium is now a 3 sodiums. But wait, that doesn't just apply to my sodium, it also applies to my hydroxide. So I had 1 hydroxide, now I have 3. Oh, hey, look, and that fixes it. 3 hydroxides on either side, 3 sodiums on either side, 3 nitrates, and 1 iron. That one is balanced. All right, so I have a little bit more room to work this out. And when you see that I post this online, well, when I post the finished PDF version of this, I think I'm going to go one step further and actually draw in the circles as well. That was recommended for last night's homework. All right, so here's a type of reaction that tends to be very hard to balance. This is one of the harder ones I will throw at you. But if as long as you follow the rules, it kind of makes sense how to solve. So let's start. Let's see, I've got a carbon, I have hydrogen, and I have oxygen. And notice that's not carbonate, that's CO2, that's carbon dioxide. It's not my polyatomic ion. Okay, so let's start counting. I've got 3 carbons, I have 6 hydrogens, I have 2 oxygens, and on the other side, I have 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. Okay, no one is balanced here to start with. But if I look back at my rules, I do need to start with one element in particular, my carbon. If you have a choice, start with carbon. So I have 3 carbons on this side, on my reactant side, 1 carbon on my product side. So I'm just going to multiply this by 3. So my 1 carbon becomes 3 carbons. But remember, this also changes my number of oxygens. So 3 times 2 gives me 6 oxygens, plus 1 more oxygen over here. So I've got 6 plus 1. I have a total of 7 oxygens. Now, normally I say once I unbalance something, once I screw it up, I then want to go and fix it. But my oxygen wasn't balanced to begin with. So I'm not going to go and focus on my oxygen. I'm going to leave that to last. So next, I've got my carbon done. So next, I'm going to work on my hydrogen. I've got 6 hydrogens on this side. I have 2 hydrogens on this side. So 2 times some number will give me 6. 2 times 3 will give me 6. But notice this also affects my oxygen. So from this compound, I have 3 times 2. I have 6 oxygens here. 3 times 1 gives me 3. So 6 plus 3 means that I now have 9 oxygens. So my carbons are settled, my hydrogens are settled, my oxygens need to be fixed. Okay, so I have changed my coefficients on my product side. I get oxygen from 2 different places here. I only get oxygen from one place on my reactant side, but notice I can only have oxygens of even numbers because every oxygen molecule is O2. They come in pairs. Well, I have 9 oxygens on my product side. I can never times 2 by some whole number to give me 9. So I can't balance this right now. As long as I have an odd number of oxygens on this side, I can't balance this. So here's what we need to do. We need to figure out, why do I have an odd number of oxygens? What's causing the odd number of oxygens? Well, if I look at carbon dioxide, in my carbon dioxide molecule, my oxygens come in pairs. So no matter what this number is, I'm always going to get an even number of oxygens here. But in my water, I get 1 carbon at a time. So as long as my coefficient for water is an odd number, I'm going to get an odd number of oxygens on this side of my reaction. So we need to change this coefficient. Now, I need to change this coefficient in such a way that I can easily rebalance my hydrogens. So what's the easiest way, and think proportions, to change an odd number to an even number? I need to double it. So rather than times this by an odd number, I want to keep these ratios. I want to keep these proportions. So I'm going to turn this 3 coefficient into a 6. 3 times 2 makes it an even number, keeps my ratio, keeps my proportions. And now I need to tally up all of my atoms. So 6 times 2 means I now have 12 hydrogens. Then I need to count up my oxygens because now I have 6 oxygens plus 6 oxygens. Oh, look, already I've got an even number, but I'm not going to go and focus on my oxygens because I had a balanced hydrogen and I just unbalanced it. So rather than go back to oxygen, I need to fix what I just broke. So I had 6 hydrogens, now I have 12. So I'm going to come back here where I have 6. I need it to be equal to 12. So 6 times something gives me 12. 2. This was a 1, so now I'm going to double it to 2. See, my hydrogens were balanced, but then I doubled this coefficient. So I had to come over here and double this coefficient as well. The 1 that I hadn't written has been doubled to a 2. So my 6 hydrogens become 12 hydrogens. Oh, wait. But now my 3 carbons is also doubled. So 2 times 3 means that I now have 6 carbons on the side. Well, I just broke another balanced atom, so I'm not going to go back to my oxygen. I'm going to focus on fixing my carbon. I had an even number, but then I had an equal number, 3 and 3, but then I doubled this coefficient. So if I want to fix this coefficient, I double it. So 6 times 1 gives me 6. Now that also changes my oxygen. So 6 times 2 gives me 12 plus 6 times 1, so 12 plus 6 gives me 18 oxygens total. So my carbons are balanced on either side, my hydrogens are balanced on either side, my oxygens are not balanced, 2 and 18. But I can finally balance my oxygens because I have an even number on this side. So 2 times some number will give me 18. 2 times 9 will give me the 18 oxygens I need. So this is one of the hardest problems that I will throw at you for balancing. But as long as you follow those rules, balance your carbon first and balance your oxygen last, it helps. It makes it a lot easier to solve. You balance your carbons, balance your hydrogens. Sometimes you get an even number of oxygens once you've balanced your carbons and hydrogens, so then you can just plug a number in for your oxygens. But I chose one where I had an odd number of oxygens because I wanted to show you how you double all your coefficients in order to get that even number of oxygens that you need in order to solve the problem. Your optional homework tonight, and again, it is optional. If you do not hand it in, you will not be punished. You will not lose any credit. If you do get it in before the deadline, you might get back some credit for homework you missed earlier in the semester. It is the reaction type worksheet that I've added in the 4-7 folder on Google Classroom. All right, in today's lesson, we had our warm-up, and we're going to take some more notes. We're going to be taking notes on the 5 different types of reactions. And instead of me doing reactions, because like you guys, I'm at home, and that's very unsafe and very not recommended, I have a lot of reaction videos. Maybe if we come back to school soon, I can actually get the materials and have a fun little demo day for us. But that is if we get the chance. So I would turn to page 3 of your guided notes. That's where we're going to start. So the first type of reaction is a synthesis reaction. So the basic reaction using A's, B's, C's, I have A plus B produces AB. A plus B gives AB. Then for your drawing of the atoms, I have this right here. Blue circle plus red circle gives me red blue. If you don't have any colored pencils with you, that is fine. You can just draw them. You could draw circle A plus, we always use A and B, plus circle J yields AJ. I produced an AJ. And to explain what's going on here, I know this is slightly out of order of your table. I have 2 things coming together to make one thing. So 2 substances, 2 elements, 2 compounds come together to make one compound. Sometimes it's 2 elements, sometimes it's an element and a compound. It might be a polyatomic and an element. 2 things or more come together to make one thing. To synthesize means to make something. And my example reaction is solid magnesium is going to react with oxygen gas to create magnesium dioxide, a white brittle solid. Now, I know that I've done this a few times in class, but it's honestly one of my favorite reactions. I have a video here that I'm about to play. This video is also in my YouTube playlist for today for the different chemical reactions, as well as I believe I linked another one in the YouTube playlist as well.
Here we have a ribbon of magnesium. Magnesium is a metal, has the properties of luster. You can see it's shiny, it's malleable, it's bendable, can conduct heat and electricity. So what we're going to do is we're going to try to react this magnesium with the oxygen in the air. We need a little activation energy to get the magnesiums to react with the oxygen, and there it is. So oxygen's reacting with the magnesium ribbon, and it's releasing a lot of light and heat energy. This is one of the brightest lights that's produced by a chemical reaction. They often use magnesium in fireworks for these bright bursts of white light. And also is extremely hot. You can get very, very, very high temperatures from this chemical reaction. Now, coming off the light, you can see a white ribbon, and that is the magnesium oxide that's being produced. So magnesium atoms are being bonded to the oxygen atoms in the air to form that magnesium oxide product. Now we have an up-close look at the magnesium oxide. You can see it has a white color. That's one of the properties. And you can see it's very brittle. Basically, it's going to turn into a powder if you touch it.
So that entire video actually goes on for a few more minutes in our YouTube playlist. It goes on to really show you how they're making this bond, how those atoms are coming together, looking at the valence electrons, how they form ions, how they snap together. So if you're interested, you can watch the full thing on YouTube. All right, our next reaction type is decomposition. So if you think about it, composition, when you're doing a composition in English class or when you're composing music, means you're making something. So to decompose means you are unmaking something. So my basic reaction with A's and B's, I have chemical compound AB decomposes into A plus B. I have my blue-red compound again, and it's making blue and red, two separate things. So if you're drawing your representation of the atoms, you could do, if you don't have colored pencils, I have square attached to circle, but then there's my decomposition reaction, and I get square free and by itself away from circle. And then just another way to describe what's happening is that one compound falls apart into two or more different molecules. It can be breaking apart into separate atoms, into separate elements, or it can be breaking apart into separate compounds. Either one can happen. The important thing is, with decomposition, I always start with one thing and I end with many things. For synthesis, I start with many things and I end with one thing. Right? And then my example here is aqueous hydrogen peroxide is going to decompose into liquid water and oxygen gas. There's a lot of different ways to demo this reaction. When you go to the YouTube playlist, you will see this video. The first 4 minutes, I will warn you, he is talking about the safety precautions to take when demoing this for students. It's the last 2 minutes where the reaction actually takes place. This one is called Genie in a Bottle. This is what I usually do once we get to this demo-filled day of class. Another one you're going to see is something called Elephant's Toothpaste. And the only reason I chose to not do Elephant's Toothpaste, which sometimes it is a little bit more exciting, it kind of explodes on everyone, is I just don't want you to fixate too much on the foam that's produced. I like you to see the gas that's being produced. Okay?
So now I'm ready to go. I'm going to find that when the reaction starts, it's going to be producing some aerosolized water, essentially some mist, but also within there there's going to be some droplets of hydrogen peroxide. For that reason, we want the audience about 5 meters away and protected behind some safety screens. And Because of that, I'm going to take off my microphone so that in order to initiate, all I need to do is take out the bung, okay, and the string will drop in, catalyst gets going. Let's see what happens.
Now, hopefully I shouldn't have to say this, but of course, don't try any of these at home. And if you have hydrogen peroxide in your first aid cabinet, it is not strong enough to do this reaction. If you have really old hydrogen peroxide in your cabinet, it might have actually already gone through this process. Hydrogen peroxide over time will break down into water and oxygen. It's just what it does. That's why some of those hydrogen peroxide bottles tend to be brown. The energy that it gets from the sunlight can actually be enough to cause that chemical reaction to occur. So by making the bottle brown, not as much energy from the sun can actually get inside the bottle and decompose your hydrogen peroxide, so it lasts a little bit longer. What I like to do if I've got an old bottle of hydrogen peroxide and I'm wondering, is it still usable? Is it still what it claims to be? I like to pour a little bit into my sink. If it fizzes, it's still good. You can still use it as hydrogen peroxide to disinfect something if you need to. But if it doesn't, then you don't quite know what's in there anymore. It might not still be good, or you might just have a very, very clean sink. But usually if you have something, usually most of our bathroom sinks, there's enough leftover residue from toothpaste and soap and what have you, that I'll usually find something to react with. All right, here comes my favorite one, combustion. So combustion's a little bit different. Not sure if we quite have circles for you to draw for this one. I'm sorry, you can't really draw the atoms, but the basic reaction here is going to be a little different than A's, B's, and C's. So what you're going to draw here, or right here, is some number of carbons, a hydrocarbon. So I can have any number of carbons. So C with a subscript of number, H subscript of number, reacts with oxygen, it's always going to be O2, to form carbon dioxide, CO2, plus water, H2O. Anytime you see fire, anytime you see flame, this basic reaction is taking place. Sometimes, depending on what's burning, there might be a few more things being thrown in there. Like here, I've got a picture of a campfire. There's going to be some more oxygens thrown into here, into this hydrocarbon. But we're never going to throw that at you, this unit. Right now, we're just going to focus on what happens when hydrocarbons react with oxygen to produce carbon dioxide and water. And then you just might, yep, there's a place right there in your notes. A hydrocarbon is any compound that contains only hydrogen and carbon. And this is also what's taking place anytime we use a Bunsen burner in our classroom. So once again, never try these experiments at home. In fact, I think I'm not allowed to do this reaction anymore at school, sadly. So I've got my methane gas reacting with oxygen to form carbon dioxide and water vapor. So again, don't do this at home. These are trained adults. And I do want to point out this woman should definitely have her hair tied back. I was very frustrated to see this in this professional video.
And so we're just going to fill the little beach ball up with methane gas. Oh, that is going to be so perfect. Look at this. So now, Tom, you're in charge of the methane gas.
I do want to point out
makes me feel better.
that the beach ball does have warnings on it.
Yeah, it's fine. That's warnings for kids.
yeah.
We're adults, for goodness sakes.
you
Now,
keep
Kim,
holding
here's
that.
what I was thinking, was that it would be fun. You know what you should do is dip your hands down in the water. So dip your hands
what's
on
in
both
this
hands.
water?
Just
Nothing?
water. Just water.
Dishwashing
And you
Okay.
are going to squeeze like this.
Okay.
Because we're going to make bubbles. So just go ahead, get all your hands down in there, way
Okay.
down in there like that. So here's what I was thinking. You put on your safety glasses like
geez.
this. This is
Okay.
fine. Do not worry, Tom. These are going to be your safety glasses.
Mine
Gosh,
are
you look
cocky.
great.
Thank you.
Good. And now,
Cockamamie.
oh, look at this, the methane
are
bubbles here.
sideways.
Now, Kim, here's what would be fun. In just a
no.
second, you are going to scoop up the methane bubbles that are highly flammable, and then I am
and
going
you're
to
gonna
light them on fire. You
That
got
sounds
it?
like
okay,
so
so
much
no, not yet.
Oh.
Squeeze some more. Squeeze some more. We need more. Oh,
More?
that is
I don't wanna do
fantastic.
that
This
much
is perfect. All right,
cleavage.
that's a good one. Would you scoop them up for me, Kim? Scoop it up. Hold your hands right there.
Ow!
Nice wide shot. 3, 2, 1. Oh. You're okay.
Okay, didn't even look.
I know.
Okay.
Isn't that okay? You're fine. Keep squeezing there.
sorry.
This is good.
Okay,
The
I'm actually
water
adjusting these so
saved
they're
you.
really
The
on.
water saved you.
Oh,
So
yeah,
look at
the
here's what
water
happened.
saved me.
The eyebrows were fine. The
come back.
water evaporated on your hands. Look into the camera and
felt
say,
warm.
"Don't do this at home.
Don't do this at home."
It's a
Or
chemistry
anywhere.
teacher
I
trick.
do
Yeah,
feel a
it's-
sense
yeah,
of
at
warmth.
school. At school, the chemistry teacher is
Don't even
wonderful.
do it on
Look at this.
TV.
The methane. Okay, now watch. You're going to scoop up the methane
Okay.
bubbles. Scoop
Again,
them up.
you're gonna do
Yes,
that?
absolutely.
isn't this
So watch
Tom's turn?
this. Look at this. This is just fine here on your hands. If I
Oh.
light it on fire, see that catches on fire. And look and show them your hands. You're perfectly fine.
I know, it's just looking
Isn't
at the
this so
flaming.
nice?
And I also want to point out real quick that she was dunking her hands into that bowl of water. That's what kept her hands from being burned. If you tried that without wet hands, then you would be burned and it would be very painful. But the water forms a protective layer to save you from those flames. And sometimes when you do it, if there's enough of a methane bubble, you actually get your hands somewhat dried from the event. Okay, but again, don't try that at home, guys. All right, our next one is single replacement reactions. I want to point out that sometimes you might see we're in a single displacement reactions. So our basic reaction here using ABCs is A plus BC. So I have an independent element plus a compound reacts and forms AC plus B. So what happened here is that my A element replaced the B element in the compound. So here, my element drawings, I have my blue circle, red circle, plus black circle. And then I get black circle, red circle, plus blue circle. So what's happening here is a metal replaces another metal or hydrogen. Hydrogen is kind of considered a metal or treated like a metal in this case in a compound. Or you might get reactions where a halogen replaces another halogen in a compound. So just a reminder, my halogens are right here: fluorine, chlorine, bromine, iodine. Sometimes acetane is also counted there. And then if you don't have colored pencils to draw this in, let's see. I have circle M, circle 2, plus circle K. Trying to mix it up here. Gives me K2 plus M in an atom. So that's just my drawing of, that's this up here. Or if you don't have colored pencils, you could also just shade them in differently. That's too big. That didn't get smaller. I got straight lines, polka dots, vertical lines, and then I end up with vertical lines, polka dots, and horizontal lines. Notice I'm trying to do lines and lines because I've got a metal and a metal, or a halogen and a halogen. And I've got a visual for you here. I've got a reaction and a visual. Poor Betty. Sorry, no, poor Wilma. So here's another visual of it. I've got Fred Flintstone plus Wilma. Then along comes Betty. Now I have Fred and Betty, and Wilma is by herself. So here it was the two women who were replaced, who were displaced or replaced. Chemical reactions can be so cruel, guys. So cruel. So my example reaction here, and this one I can't always do because this one uses actual silver, and so it's actually kind of expensive to do. I'm going to have some solid copper reacting with some silver nitrate solution, or aqueous silver nitrate, and it's going to give us solid silver and then a copper nitrate solution, so aqueous copper nitrate. Here it goes. And in our YouTube chemical reaction playlist, we have this one along with another one that shows it. It's great. I love the way that the silver grows. Now also notice the color of the solution right now. It's kind of a grayish solution. Now my copper, it was nice and bright and orange. Now it's very tarnished, very black. You can start seeing there's my silver precipitating out, my silver crystals starting to grow. And if you look at the solution, it's starting to turn blue. Copper nitrate is a blue solution, like from the penny demo yesterday. So the solution itself goes from kind of a grayish color to a bluish color. You don't need to worry about oxidation and reduction right now, what it's saying there. But look at that, it grew silver. The other video I'm going to link to in the YouTube playlist uses a copper wire. And how that ends is it kind of looks like a big fuzzy caterpillar. So I always enjoy doing this one at school. Now, the next part of the table says, how do you tell if a reaction took place? Because we don't always have our reaction take place. Now, in a normal school year, the next day that I teach you these different reactions, I would give you a full day on nothing but single replacement reactions. But the atoms here, whether or not they get replaced depends on who is more reactive. So we have something called an activity series. And it's only going to happen if the lone metal is more reactive than the one that's in the compound. So here, if I look here, silver, Ag, is in the compound. It's all the way at the bottom. But my copper is above it. So my nitrate, it's kind of like it's nitrate's choice who nitrate wants to be with. It can be with the silver, or it can bond with the copper. The silver is a much lower priority. It's lower on the list. It's a lower priority than the copper. So rather than stay with the silver, my nitrate decides to bond with the copper instead. So if I go back to the Flintstones, who do you think, Wilma or Betty, who do you think was lower on that activity series? It was Wilma. Betty must have been higher on that activity series. So Fred was no longer bonded to Wilma. He now has chosen Betty. Betty must have been higher on the activity series than Wilma. All right, and then our last reaction for today is double displacement. So in double displacement, two metals are switching places in compounds. So my ABC version, I have AB plus CD, and it's going to yield AD and CB. Now there's a few things I need to point out about this reaction, about how I wrote it out. Notice A and C came first in both of their compounds on both sides of the reaction. I always write my metal first. So if A and C were my metals, it's my B and my D that switch places. So my blue and my black elements were still in the front of their new compounds. My green and my blue are the ones who swapped. And because I just love the groans that this gets from my students, and I'm so sad I can't hear you guys from home when I turn to this page, I have Justin Bieber and Selena Gomez, then Taylor and Taylor. I made it TS so we know which Taylor I'm talking about, Taylor Swift. And then we swap partners. Now it's Justin Bieber, Taylor Swift, and then Taylor Lautner and Selena Gomez. So they switched places. But apparently the boys are the metals here in these. Well, actually in the pictures, they're just the one further to the left, so they became my metals. So it's the girls who swapped. And then my example reaction. I believe we actually did this earlier in the school year when we did the different physical chemical changes lab. I'm going to put potassium iodide and mix it with lead nitrate, and it's going to form potassium nitrate, which will still be in solution, and lead iodide, which will be a solid. So aqueous potassium iodide and lead 2 nitrate react to form aqueous potassium nitrate and solid lead 2 iodide. That's finishing out my word equation. And now I'm going to play it. Something to point out is that both of these solutions start out as clear solutions. And when I end, potassium nitrate is also going to be a clear solution. So something to point out, as they're mixing the two chemicals, it's not making a yellow solution. You can see the little dots of yellow right there. It's making a solid. So this is really neat. They're making a water bridge. So as those ions are floating towards each other, look what starts happening. Where those ions meet up, they start to precipitate out and to make a solid. So to describe what's happening in words, you can say that two different metals swap their non-metals. But what's really going on, if I look all the way into the chemical reaction, what I have is 4 different ions, because remember, ionic compounds dissociate in water when I make a solution. So I've got 4 different ions floating in solution, and if I have a reaction, so this is that last box, how do I know if a reaction takes place? It's only really a reaction if 2 of those 4 ions decide they'd rather come together and form a solid and precipitate out of solution. So here, my lead and my potassium ions, made a solid. My potassium and my nitrate ions, they started as ions floating in solution, and they're ending as ions floating in solution. So you know that a reaction takes place because a solid is produced. So you know a reaction takes place because a solid is produced. If I mix two solutions and there is no solid, I end up with two solutions. Well, I started with 4 ions in solution, and I'm ending with 4 ions in solution. So sometimes it doesn't take place. It only takes place if a solid is produced. And just like how I said that normally after single replacements, I'd spend an entire day just focusing on deciding whether or not single replacement reactions took place, I would normally spend an entire day on just double displacement reactions. There's a chart you use to see what will and will not dissolve in water. But for this week, all you need to be able to do is to be able to see a double displacement reaction and label it as such. You have to be able to see this and say, that's not combustion, that's double displacement. That's not single replacement, that's double replacement. And another quick word, it can be written as double displacement or double replacement. All right, well, that is all 5 types of reactions that you're going to see on assignment 1. The homework, again, it is just practice identifying those types of reactions. It is optional, but it will really, really help you in the long run if you do it, or heck, if you even do half of it. Practice is what you got to do until it makes sense. You might think this all is very straightforward, but until you practice it, you just don't know how well you really know it. Okay, so I hope everyone is doing well. Stay safe, stay indoors, except you can go outside to exercise. Just stay 6 feet away from everyone. I hope you're all safe. Have a good one. Bye.